little bit. Okay, assalamu alaikum. So last class we stopped at the master diagram, and I'm gonna go to the next one. Just we have multiple examples for the master diagram. I'm gonna say one only, discuss one, and it is amazing, this master diagram. You would imagine that you have everything in your hand if you have a master diagram for every single material, but it is mostly for steel, as we know, because steel was very important, until now is a very important material. So let's say that is the example that we had before was for AISI steel, and it is 4340, very common steel in machinery, and its ultimate strength is 1100 megapascal, and the yield stress is 1225. That's a lot of yield, huh? So now what are we looking at is that I'm going to show you here how to use the master diagram. In this one, it says at a life of 10 to the power 5, okay, cycles, which is 100,000 cycle. What is the allowable alternating stress for a mean stress of 50 kbsi? This is in kbsi, not in megapascal. So you can see here is that I want 100,000 cycles. I must apply a mean stress of 50 kbsi. Now tell me, yeah, designer, tell me what is the amplitude that I can apply. You may tell me you can apply this much or that much, and that's what I wanted. So what do we do? Okay, look at the curve. Here, what do we have? We have the life curve, the constant life curve for 100,000, which is this one. I'm drawing it in green. Okay, and then what I'm gonna do, since the mid-range is in the inclined axis to the right and the alternating stress is on the left, so what I'm gonna do, I will go to the mid-range here. The question says for 50 kbsi. So I'm gonna go for 50, that's 50, and then I will draw a line until I intersect the life I wanted. You will intersect 10 to the power 6, you will intersect 10 to the power 5, 10 to the power 4. But what your intention is to go for 10 to the power 5. So what do? That point now, all what you need to do is to draw a line perpendicular to the other axis, passing through the intersection point, and there you go. You will see the amplitude. That's the amplitude. If you combine it with this mean, you will get a life of 100,000. Very simple question. Another one, at a life of 10 to the power 4, what is the allowable alternating and mean stress? Both. I need both if the R ratio is 0.2. So what I am going to do here, I will go and draw a line from the 0 here. Sorry, the line should go like this. This line corresponds to an R ratio of 0.2. Now, at R ratio 0.2, the line, again, would intersect 10 to the power 6, 10 to the power 5, and 10 to the power 4. Now, once I know I want this point, خلاص, what need to be done? This and this. عرفنا إنه الميد range is 90 kbsi. And what is the amplitude? 60. Do this, you get what you want. You want the minimum and maximum? Of course, you can just go like this and like that. That's it. Do you get that, ya shabab? It's a very simple, straightforward. So you need just to understand what are the givens, and you need to understand that for minimum and maximum, you use horizontal, vertical. For mid-range and alternating, you use these two. And in order to reach to this one, you need always to shoot from the 0 here at a different lines. That's what you need to do. Very simple. Yes.
If he says -1, ratio -1, should we go
Yes,
from the left axis?
Yes. This is the R. Yeah, what is it?
If the given said the ratio is -1, should we go horizontal from the -1 on the left axis? Because R is written here as -1 until we cut the cycle, the lifetime curve.
Okay, you mean here? For example, what is this? Is that what you mean?
Yes.
This one would become, I think it is, I think this one is going to continue, that this is 120, and this one supposed to be 140, this one 160, and then 180. The R ratio here and A indicates another thing. Let me check it, okay? And then I will comment on it in the next class, okay? I want to see why they're putting it right here. We know that R ratio and A ratio are on the top, okay? You got my point?
Yes, thank you.
But yeah, I can see the R ratio of -1 is indicated on the left side, while it is not indicated on the top over here. So I'll check that. I'll see. Okay, now what are we gonna do? We are gonna move to the design equations. When I say design, automatically you should understand that there is a factor of safety. Okay, now for mean positive mean stress، أهم حاجة يا شباب تتذكرون إنه هذه المعادلات for positive mean. إذا كان negative, we'll have a different condition. We said we should compare SA with SE, the amplitude with the endurance limit. That's what should we do. Now, if we want to write these equation as a design equation, as you see, we will employ the factor of safety, which is 1/n over here, 1/n, here the factor of safety is employed right there. Why is that, ya shabab? Why? Very simple, because the factor of safety, if you want to apply it in a stress equation, what did we say before? We should multiply n by sigma A, and for example, for Söderberg, divided by SE, and then n by sigma m divided by SE, which is equal to 1. So if I take n as a common factor, I will cross this and divide by n. I will have the equation like this. But in here, for example, when I multiply the n by a factor of safety, n will become n squared. So there is no point of taking a common factor. Do you understand? That's why n here is also squeezed inside, and this is equals to 1. I hope you understand why is that, okay? It's simply because we are going to replace SA and SM with with sigma n multiplied by n, and with sigma m multiplied by n as well, okay? Now, for design purposes, we know that you might want to program your design equations, and you want to know always what are the results coming from different criteria. And what did we say? If you recall, let me go back to the curve over here. As you see, we have multiple intersections. So, for example, just to tell you, a design line, this is called the load line, okay? The load line, if you think about it, it has a slope of SA divided by SM. Why? لأنه يا شباب السلوب هو what? السلوب معناه إنه there is a curve, okay, inclined. Its angle, its slope, is related to the ratio of y divided by x. Isn't that true? It's true, right? Tan, if you think about it, the theta, which is the slope, if you think about it, it's related to the tangent of y over x. And this is like y because in the y-axis, and this is like x. So if you look at this line, this is an equation for a line. This line has an equation which is r, the slope, is equal to SA over SM. At the same time, this Langer line has an equation also which has SA and SM. The Gerber has a line, Goodman has a line, elliptic has a line, Söderberg has a line. So basically, as we learned from calculus, the only thing you need to do is to take one equation and you make it equals to another equation, and then you will find the point of intersection. The point of intersection ايش راح تكون؟ راح تكون where do they intersect with M? Where do they intersect with A? فمثلا على سبيل المثال لو لاحظنا النقطة هذه, this is the point between the elliptical equation and the load line. And the intersection with SA, which is sigma A, and sigma M, is this line. So if I take the equation R equals to SA over SM, and I equate it with the elliptical equation, I can solve the equation for X, and I then substitute it to find Y. These two coordinates are the intersections. Now, this is very nice because you will always determine, based on the intersection, where are you from each criterion. So this table, we have multiple tables between, for example, look, between Goodman and the load line. Look, what are the intersections between Goodman and the load line? It is SA, which is RSE multiplied by SUT divided by RSUT plus SE. And what is SM? It is SA over R. Okay. And then between the Langer line and Goodman. So you want to know when Goodman and the Langer line is the line of yielding, they intersect. And what is the coordinate of that intersection? This is very interesting if you want to program it. Then we have the same for Gerber. طبعا احنا دائما ودنا نعرف التقاطع ما بين الكرايتيريا, which is Gerber, Söderberg, Azmi elliptic, and so on. So between the criteria and the Langer line. Why? لأنه Langer line يا شباب indicates the yielding, which is very much not needed and dangerous in fatigue. And then the intersection with the load line. يا شباب in fatigue, most of the time, عندنا general rule. لما يجي طالب تو يتعلم يعمل fatigue testing, يقول لك أنا الآن سويت 100 عينة. I want to start testing them. Where should I start? What should I put? 100 Newton, 2000 Newton? Where? The general wisdom إنه نقول له روح شوف الماتيريال and look at the yield stress and then find the strain there or the load. If you apply, listen to me carefully, if you apply an R of -1, which means the maximum is the same as the minimum in magnitude, but with negative sign, as an amplitude, if you apply the yield load as an amplitude, you will probably get no more than 1,000 cycles. no more than 1,000 cycles. Can you believe it? يعني يا شباب, the stress strain curve is like this, very big. It can reach to 20%, 40% strain. احنا ايش نقول؟ نقول at the yield which could be less than 1%, you know, maybe 1% maximum, 1% of strain only. If you apply this load in a cyclic fashion, you will probably get 1,000 cycles, no more. Probably. That's a general wisdom. طيب وين المصايب تصير لما when you have tests that runs for months, you are here, you're probably here, you go down. So this is very strange. This tells you, يا أخوان, why fatigue is mysterious. You are cycling here in the elastic region, very low, yet you get failure. We always think that failure is associated with the plastic deformation because it's permanent, but it is no. Everything in fatigue happened here. ما في حد يعمل cycling at this level. كم حتحصل؟ 2 cycle, 10 cycle, ما تسوى. لا تضيع العينة يعني. So this is the relation with ME-elliptic as well. Okay. طبعا ما في intersection مع Söderberg يا أخوان because of this. Söderberg is alone. Look at it. Oh, I'm sorry. The Söderberg is alone over here. And it intersects with yielding when you apply yielding. That's it. So yes, you might want to know what is the relation or the intersection between Söderberg and the load line. This wasn't done, but it's different than other criteria. Other criteria may even intersect with each other. Okay, they get you the same value while some other are not. Okay, now one last thing is this. We talked about failure, okay, in materials which we characterized by what, ya shabab? Yielding, SY. We saw that, for example, Gerber consider yielding as an intersection with the mean stress axis. And we saw Goodman talking about SUT. We saw ME-elliptic talks about yielding. And the truth is, ya akhwan, I'm just telling you, I just told you that the yield is too much. So ultimate is way too high for cyclic fatigue, okay, for cyclic loading. So those are all ductile materials, yeah. But what happens if you have a brittle material? A material which is brittle. There are materials which are brittle and they are very useful. Ceramic is one of them. We use it a lot. There are some cars that have their fuel valve, يا شباب, the valve اللي open the compartment for the air, and the one which is open the compartment for the fuel to get inside the engine. We know that some cars have these little tiny gates valve. The valve is like this, okay? I forget their name. It's like this. When they are like this, nothing can get inside. When they are down, when they go down, ya shabab, the gate open here and then the fluid goes inside. طبعا, why do we use, I heard, ya shabab, one time that they use ceramic material because it doesn't expand a lot or contract with heat. We know that, you know, brittle materials, that's why ceramic are used a lot in high temperature application. They don't shrink or expand a lot at heat, and this will make the engine more efficient. And if you think about it, while this is opening and closing, there are forces, there are cycling happening. So in general, ya shabab, Your teeth, by the way, are, I think, fairly brittle material. And just remember how many times you chew. كم تعض يا شباب وانت تاكل, and for how many years. That's enough cycling. And when you go to a dentist, يا شباب, he will talk about fatigue with you. He will talk about fatigue with you. Because when they put implants, when they put fillings, and they fail due to fatigue failure. You just munch and munch and munch, and then there are يعني يا شباب, I cannot remember how much is the force we are putting, but it is not little. It's a lot. Remember that some people can bite other people and rip off their meat, huh? Their skin. So just like Mike Tyson. So what is interesting is this, that brittle materials, ya shabab, actually not like ductile material. Turns out that in ductile material, we were seeing that the relation between the amplitude and the mean is curving down. Actually, based on your textbook, it says that the brittle material actually has this concave up behavior. Do you understand? So it is totally different. Now, we have only one equation in your textbook which proposes to relate the strength of the material as in terms of fatigue between for brittle material. It is, which is known as the Smith-Dolan equation. And it is written in front of you. It is SA divided by SE. Again, SA is the ultimate strength, is the amplitude strength divided by the corrected endurance limit, and then equals to 1 minus SM over SUT plus divided by 1 plus SM divided by SUT. This is the equation when we replace SA with N sigma A and SM with N sigma M. And this is the intersection between the equation and the load line, okay? But one equation only, that's all what we have. Now, if you have the, ya shabab, for, as you see here, it says that the most likely domain for designer use in the range of sigma M, which is the mean stress, which is between SUT and minus SUC. That's more than this is nothing, okay? The locus of the first quadrant is Goodman, Smith-Dolan, or sometimes in between. So what is it saying here is that the portion of the second quadrant that is used to represent, that is represented by a straight line between the point SUT, I think I am repeating here, and this one is SUC, is given by this equation. So basically, what are we saying here is that for cast iron, ya shabab, which is not like ceramics, but it behaves like a brittle material, okay? For SM, the mean strength or the mean strength is less than 0 and it's greater than SUT, you can use this equation. Only one, okay? So we will now start a quick example. I hope we can have time to do it. This is a very interesting example. It doesn't involve, okay, positive mean stress. I intentionally made it here to teach you how to deal with notches at the same time with the negative mean stress mostly. And then we will have example about positive mean later. So this figure shows the free body diagram for a connecting link portion having a stress concentration at 3 different locations. The locations are this one, and this one. Of course, this part is the same as this part, which makes it easy. So we need to analyze one of them only. The dimensions are given. R is given to us, W2, W1, and the diameter of the hole, which and the H, which is the thickness, as well as the diameter of the hole. Now, what we know is that there are fluctuating loads between 4 kilopound and a compression of 16 kilopound. So we have a load which is going like this. This is 4 kilopound, and this is minus 16 kilopound, and the load is fluctuating in between. All right. Now, what do we want to do? It says neglect column action, meaning that please don't talk to me about, oh, this is gonna buckle or not. Just focus on the factor of safety. If this material is made from AISI 1018 steel. Okay, so the idea here is that what are we gonna do? Let me just pull up the solution. Or yeah, Shabab, let me get rid of the attendance quickly, and then we will talk about the solution for this problem. Faisal?
Yes.
Yes. Yusuf?
موجود.
Ahmed? Hamad?
Yes.
Khamis? Ali? قحطاني?
Yes. موجود.
يوسف؟
Yes. موجود.
اليوسف. ماجد؟
Yes.
حسين العلي. Okay. محمد. محمد, where are you? Yeah, Muhammad, you are here. Can you talk to me? Okay. Hassan, Ayash, you're here. Mubarak, Mubarak.
موجود.
دوسري. Ahmed, Ghazali, الحاجي, I can see you.
موجود دكتور.
معجب.
موجود دكتور.
Okay, I see you. Sultan.
Yes دكتور.
No, Abdullah
Yes.
الحجاب. Sultan is here. عبد الرحمن. عبد الرحمن. خالد العتيبي.
Yes.
عبد الله العوفي.
Yes.
and فارس القحطاني.
Yes دكتور.
ثابت.
Yes دكتور.
علي رمضان.
موجود دكتور.
Yeah, I can see you. هاشم.
Yes.
ماجد.
Yes دكتور.
محمد.
Yes, doctor.
and أحمد سلطان.
Yes.
مشعل اليامي.
Yes, دكتور.
وليد.
Yes دكتور.
محمد بارشيد.
Yes دكتور موجود.
عبد الله.
Yes, doctor.
أحمد.
Yes دكتور.
Okay, thank you يا شباب. So let's get back to the lecture now. We're having the problem. Stop.
دكتور تسمعني؟
Yes.
بس دكتور قاعد يقطع عندي ما حضرتني بس.
Where were you?
I was in the class بس قاعد يقطع عندي الصوت مرة.
What is, oh, let me see. أنت عبد الرحمن. Okay. Okay. So let's get to this problem, ya shabab. So what are we going to do in here? Let me show you step by step. We will get rid of the endurance limit because this is now under cyclic loading. So we go to the table A20, and then we get SUT. We got SUT. It is 64 kbsi. That's less than 200, if you remember. SY is equal to 54 kbsi. Okay. Now, if this is less than 200, then SE prime. Let me wait a second. Forgot to switch on my webcam. So so SE prime is equal to half of 64, which is going to be 32 kbsi. Now we go to the next one, which is Ka. This material is cold drawn. If it is cold drawn, and remember this is in kbsi, so this is going to be 2.7 multiplied by SUT 64 to the power minus 0.265, which is 0.897. Now, what is KB? It is equals to 1. Why? Because the size factor, if you remember, we said this is the surface factor. The size factor become equals to 1 if we have axial loading. We have cyclic axial loading. Now, what is Kc? Kc is equals to 0.85. Why? Kc equals to 1 in bending. It is equals to 0.85 for axial and 0.59 for torsion. Now, that's it. Nothing about temperature, nothing about reliability. So what we are going to get, we're going to get SE, the corrected endurance limit, as 0.897 multiplied by what? 1, which is KB, multiplied by 0.85, which is KC, multiplied by SE prime, which is 32. And what did we get? We get 24.4 kbsi. Good, ya shabab. Now we are done. Now, what are we going to do then is to go to the notches. First, to the fillet. Now here you need to be very organized. Why? We go to table A15.5 for what? For a fillet. And then when we have a fillet, we will find that the capital D is equal to 3.75, small d equals to 2.5. Of course, this is in inches. And d over d is equal to 1.5. 1.5. Now, what is r? Small r over d, the radius of the fillet divided by the small diameter, it is equal to 0.1. Now, if we go to that A15, you will see that you will have d over d as a, I don't remember the curve, honestly. It's d over d, and then probably r over d, and then you will know what is kt. Sorry, this one is supposed to be kt. I think, if I am not mistaken, this is d over d, and this is r over d, and then when you hit the curve, you will find kt. Now, what is kt? Kt is going to be equal to 2.1. Good. Now, when you find kt, all right, what do you need to do? Is to do this. R is equal to 0.25. So I need to go to figure 620 to get Q, which is how much? 0.82 for the ultimate strength that I have for the material, and with the radius, which is 0.25. Now, if I do this, I can find Kf, which is equal to 1 plus Q multiplied by Kt minus 1. So this is going to be equal to 1.9. Good? Now, I found for the fillet, what is the fatigue stress concentration factor. Now, I need to go and find the maximum stress. We were told we have 4 kilopascal, 4 kilopound divided by the area. The area is 2.5 multiplied by 0.5. And then this is going to be 3.2 kbsi. Then I will find sigma minimum, which is minus 16 divided by the same area, 2.5 multiplied by 0.5. And this one now is minus 12.8 kbsi. Good? Now, what is the amplitude? This is what I need. Sigma A is equal to, if you remember, the amplitude was supposed to be equal to sigma max minus sigma minimum divided by 2. But what I'm going to do, I don't need to forget to multiply by Kf. Kf is going to amplify the stress. So better to include it here and get rid of it. Now, this is going to be equal to Kf, which is 1.9, multiplied by sigma maximum. Sigma maximum is 3.2 minus 12.8 and divided by 2. This is going to give you a sigma maximum of 15.2 kbsi. Sigma minimum, ya akhwan, is equals to Kf and sigma means, sorry, multiplied by, ya shabab, sigma max plus sigma minimum divided by 2. And if I do this, what would I get? I will get minus 9.12 kbsi. Now, next class, shabab, this is the end of the lecture. Next class, we will finish this problem, and then we will talk about multi-axial loading and shear. And we will, inshallah, we will finish the chapter. Okay, thank you so much.